Proceeding with refraction, we're looking at applications of total internal refraction, and we shall review the number we did at the end of our lesson last Saturday, which is in the background already. But before we start our lesson as usual, I want to thank everyone out there that is following up with the teaching, the different teachings on different media houses. And I want to say a few words to inspire the students that are following this lesson. One writer said that winners don't quit and quitters don't win. I want to say that winners just do it. Of course, most losers just think of it, but winners, they just do it. I also want to tell the students out there that it is not the size of the dog that matters in the fight, but the size of the fight in the dog. I like that saying. It is not the size of the dog that matters in a fight, but the size of the fight in the dog. What does that mean? For those that will be successful academically or otherwise, it may not depend on your physical size, but it depends on the determination in you. It depends on determination in you. It may not be the school that you attend that will matter in your ability to excel as a student. It depends on how thirsty you are to look for information wherever it is, from your networks. If you appropriately look for the right information and use it very well, I can assure you that you will attain success as a candidate out there. And if there is something to gain and nothing to lose by asking, I will always encourage my students to ask. If there is something that you are going to gain by asking and nothing to lose by asking, please ask. And I always say that ask is an acronym that stands for always seeking for knowledge. My dear students, never hesitate to ask. I've seen adults struggle even in public transport when they are going where they don't know, and they fear to actually ask the conductor. They fear to tell the conductor that I'm going to place ABC, but I don't know where it is. Why should you be shy? If you don't know, always ask. We start our lesson by looking at the number. This was the original diagram. In the question, I have not put the question, which I am sure you have. But the question was saying that if the incident ray is rotated through an angle beta, if it is rotated through an angle beta, they were asking us to prove or to show that the sine of, they're asking us to show that the sine of C times the sine of beta, because the angle of rotation was beta, is going to be given by the sine into C minus alpha. We are supposed to prove this. There could have been a mix-up as we did this number. That is why I want to emphasize it. I want us to focus on this triangle here. I'll call it triangle ABC. Triangle ABC, if I draw it out here, it looks like this. Remember, I always tell you the major function of the brain is to forget. And I want to pick this point because it is of interest. This is the point I'm calling B. And of course, we have this point that I've called C. Now, we have our normal here as well. And I want us to get these angles very well. Because at this point, which I've called B, this angle is 90 degrees, and this is the refracted ray going. We saw that the angle that is responsible for causing the refracted ray to graze the interface is the critical angle. And if it is the critical angle, it means this remaining angle here becomes 90 minus C. It becomes 90 minus C because the whole of this is also 90 degrees. Now, as you can notice here, this angle is the angle of refraction, which I am going to put here. This angle here is R. It is R. Now we want to find out the value of R. We want to find out the value of R. So I will use this triangle to find the value of R. How? If I'll find the whole of this value, because the whole of this value should have a different angle. If we get the whole of this value using triangle ABC alpha plus 90 minus C, this angle plus that angle plus the whole of this angle, if I called it A, let me call it P. If the whole of this angle is called P, should be equal to 180 degrees. But ideally, if this is 90 minus C, this is alpha, and this is P, we are saying P, if we make it the subject, will be the same as 90, this 90 subtracted from 180, plus C minus alpha. 90 plus C minus alpha. But this P already has an R there. So we want to find out, how do we bring in the R? How do we bring in the R? Since from the diagram, the whole of this angle is actually 90, this other angle is 90. It implies that P is actually the same as 90 plus R, because this is a normal here, which indicates that this angle is 90, and therefore this other small angle is an additional 90. So if P is equal to 90 plus R, when we put it there, we shall say that 90 plus R will actually be equal to 90 plus C minus alpha. Our interest is to find the value of R. This 90 will cancel, and therefore the value of R will be equal to C minus alpha. That R is very important here. Our R is C minus alpha. Now, we want to consider refraction here. Remember, the refractive index of the prism is N, and the angle here is gamma. If we are going to consider refraction at point C and refraction at B. At point which I have called B, at point B, if we consider refraction, the use of n sin I is a constant, will give us the refractive index of this glass times the sine of I, which is the critical angle here, should be equivalent to the refractive index of air outside here times the sine of I, which is 90 degrees. But we already saw that the sine of 90 is 1. The sine of 90 is 1. So, and the value of n air is also 1. So it implies that n, the sine of C, is actually equal to 1, from where we can have our n as 1 out of the sine of C. We can keep this equation here because we shall need it. Remember, we are supposed to show this. Now, if we consider refraction at point C, refraction at point C, point C is this point here. The angle of incidence is the angle of rotation of the incident ray, which is beta. So it is n air, the sine of beta. Because at point C, our I is beta, and our R is R. NA, sine of beta, should be equal to the n of the prism, or the triangle, times the sine of R, times the sine of R. Remember, we already know the value of R here. And we already know that NA is that. But from here, from star, we know the value of N. So if I substitute in my value of N here, it implies that this is 1. The sign of beta, because the N of A is 1, should be equal to N, but N is 1 out of sine of C times the sine of R. But we also know R previously that R is C minus alpha. So if we feed in and rearrange this, our sine of beta will be equal to 1 out of the sine of C times the sine of R as now C minus alpha. And if I cross multiply through by sine C, both sides, multiply sine C, our sine beta or sine C times the sine of beta will now be equal to the sine into C minus alpha as required. We'll now be able to show that actually sine C times sine beta is equal to C minus alpha as was required. As was required. It is always important, like I always tell students, to keep practicing, because these numbers must be able to come out very well. They must be able to come out very well without any hassles. I think there was a mix-up as we concluded, but wherever it was not clear, you must have got it right now. The reason why I sometimes put these extra diagrams, because this is a lesson. In an exam, you go straight. If you have the facts, just go straight, because here I am teaching. I am teaching very many students from different backgrounds, and therefore, by default, some may need that extra explanation. Some may need that extra explanation because we have different levels of understanding. We shall be proceeding, as I told you now, to look at the next part. Yes, we have been using prisms, but now we are going to officially launch our start on prisms as our main or major new discussion in today's lesson. I'll give 2 minutes, approximately 2 minutes, for those that are capturing this working to finalize the capture. And remember, I always tell you that the major function of the brain is to forget. Biologically, I could still say it is true that the major function of the brain is to forget. If the brain was not forgetting, we would not be repeating several concepts even after assessing them in school. If the brain was not forgetting, no one would ever forget anything. And the reason why we teach and we give exams, we give tests, we are checking whether the brain still remembers. And those of you, I think all of you out there, whether you're a student or not, you have been in class before, and you know very few people in class usually get 100%. That is just enough to clarify that we do forget. As we continue to enjoy the lesson, I hope my learners, you are not just listening to the information that I'm sharing, but I am sharing this to keep you busy, but at the same time to allow you copy what is written here. However, I want to say that I always challenge and tell my students that I'm the only person that can write and talk at the same time. I'm the only person that can write and talk at the same time. There could be others out there, but not my students. It is very, very difficult for a student to write and talk at the same time. I want to assume that you are through, and allow me to take you to the next part of this lesson, which is talking about prisms. I remind you, Teacher Kakuri is still in the house, and please enjoy the lesson. prisms is what we are going to talk about next. A quick drawing of what a prism looks like would actually look like this. Would actually look like this. I could use this as well. I could use this as well, but let me adjust it. I think it will look better when I draw it this way. Yeah. If I put this line to connect over there, and I put this to connect over here, and I put another line right over here, and I let this connect here, and let this connect here. I have a simple prism right over here. I could put another one running from here to there, and put another one running from here to there, and put another one to connect these 2 points. For those that have seen how a prism looks like in the lab, that is exactly what it is. I could say this is A, B, C, D, E, F, G, H, I. If we go to the mathematics, not the physics, but the mathematics of shapes, then we actually look at, it's a very, very nice looking glass. It is purely glass, but it is a triangle. Wherever you press it, it will be triangular. Whether you make it sit on plane ABG, it will still appear triangular. Whether you make it sit on EDH, it will appear triangular, and so on. This is what we call a prism. And to be very brief, I will say that a prism, it is a transparent, as I've said, is a transparent piece of glass. It is a transparent piece of glass. It is a transparent piece of glass with 2 planes. With the 2 planes. In 3-dimensional mathematics, we call them planes. AB, D is a plane, and all these are different planes, but we are saying with 2 planes intersecting, the 2 planes are intersecting and inclined to each other, to form what we shall call uniform cross-section. To form uniform cross-section. So if they ask us to talk about what a prism is, we are saying it is a transparent piece of glass with 2 planes intersecting and inclined to each other to form a uniform cross-section. Now, if you look at these 2 triangles, ABG and EDH, if they are connected by GH, this could be a different letter. Then we are saying that AB and ED intersect along GI, and they form a piece of glass. They form a piece of transparent glass. Very nice looking feature. And what do prisms do in physics? What are the uses of prism in physics? We shall point out three major uses. We shall point out three major uses, and we have already seen some of these. We have already seen some of these. If you may remember our discussion of applications of total internal reflection, one of them was the inverting prism binoculars. So we can say that they are used in prism binoculars as inverting prisms. Used as inverting prisms in binoculars. In binoculars, we saw that a prism binocular is able to totally internally reflect light and form an inverted image of an upright object, or vice versa, depending on where the light is coming from. Two, they are used in the determination of refractive index, used to determine refractive index in a spectrometer, and the refractive index should be of glass in a spectrometer. The instrument, the special type of prism used here is a spectrometer. Hopefully we shall be able to discuss it in another lesson as we proceed. And the other use of a prism, if you may remember, on days where it is threatening to rain, you normally see what different tribes would call a rainbow, or someone would call maybe a spectrum, depending. But prisms are also used in the dispersion of white light, in dispersion or splitting of white light to form a prism, to form a rainbow, but we shall call it a spectrum. So they are used to disperse white light, and in the process we can obtain a prism. We can obtain a spectrum which is under normal circumstances referred to as a rainbow. In brief, this brings out our introduction of what a prism is, and we shall begin by looking at how does it refract light. Refraction of light by a prism. Refraction of light by or through a prism. Just like we have been looking at refraction on plane surfaces, we are going to note that a prism has special features, and this introduction part of any concept in science, especially in physics and maths, which I know how to teach best, the introduction bit is extremely important. We shall have this angle referred to as A, and we shall call it the refracting angle of the prism. It has a special name called refracting angle of the prism, and the symbol we normally use for that angle is A. We shall consider this surface as the refracting face, just like we are looking at plane refraction of light. Light incident here will be incident, and we shall consider this as the angle of incidence on that face, this face here. This is going to be considered to be a normal, so we assume that is 90. This light will be refracted. This light will be refracted, and we usually emphasize that for you to be able to show that there is refraction, there should be an appearance of bending of light as per the definition. Refraction is the bending of light. If this is I1, we shall call this R1, meaning that it is the first angle of refraction. To make this a ray, we shall definitely put an arrow. At this face, we shall have another normal, and light will definitely come out. Again, refracted. Now, this angle of emergency, the angle of emergency can also be referred to as the angle of incidence if we use reversibility of light. So I'll call it I2. I'll call it I2, and therefore refer to this as R2. Refer to that as R2. I will extend this because I need to illustrate a few more other things. So let me make it bigger. As we begin, if I extrapolate this normal, if I extrapolate it and also extrapolate this one, such that they meet there, by angle geometry, the candidates following this lesson should know that this angle remains the same as the glancing angle of the angle of refraction of the prism. It becomes the angle of refraction of the prism. And from the properties of angles, we say the sum of two interior angles will give you an exterior angle. From the properties of angles, we note that R1 plus R2 will be equivalent to A. From angle properties, we obtain that R1 plus R2 is equal to A. The sum of two interior angles, R plus R2, should be equal to A. Now, that is one thing. If we extrapolate this incident ray, in other words, if light was able to pass without refraction at this point, this would be where it would go. And the whole of this angle would be opposite to this angle, I. The whole of it would be opposite to this angle, I. But this value here, this angle here, is going to be called D1. It's going to be called D1, and we shall call it the deviation, the angle of deviation. I'll probably emphasize that in an emphasized diagram shortly. Similarly, if this angle is extrapolated without any refraction at this point, this would equally be D2. It would equally be the deviation on this face. And this angle now they form, we are going to call it the total deviation. The total deviation. D, or we can use small d. Now, from these triangles, let me call this point A. No, let me call it P to avoid the clash of letters. I call this Q, and I call this R. That using triangle PQR, we yet have another equation that D is another exterior angle, and it is equal to the sum of two interior angles there. D is another exterior angle, and it is equal to the sum of two interior angles. Emphasis before I summarize, I want to emphasize this, that if we have this as our normal, we are saying this angle is I1, and if it was to pass without any refraction, it would pass like that. But if this ray is refracted along there, then assuming that this is my normal over here, we have said this is I, this would be R1. This would be R1. And we are saying this would be D1. And clearly, one would see, we are saying that I1 is actually equal to R1 plus D1. Plus D1. That this angle would be equal to the whole of this angle. The whole of this angle. This angle would be equal to the whole of this angle here if there was no refraction at this face. And this implies that D1 would be equal to I1 minus R1. Similarly, if we tried out the same at this point, this is at P. At P. P is this point here. That this angle I1 is equal to this, much as this appears to be bigger on the diagram. But you see, if this is the normal and this ray is going like this, these are vertically opposite angles. Vertically opposite angles. And similarly, we would say at Q, I2 would also be equal to D2 plus R2, implying that D2 would actually also be equal to I2 minus R2. D2 would actually also be equal to that. That is very, very important in the journey we are beginning to take here. That is very, very important in the journey we are beginning to take. And I always say that it does not, I said it is not the size of the dog that matters in a fight, but the size of the fight in the dog. If we consider this as M, we have the incident ray. A ray which I now call MP, that is the incident ray. Incident in air, it is coming from air to glass on a prism. It is incident in air on a prism of refracting angle A. Whatever I'm writing here, you already know and you can refer to. The prism has refracting angle A. If I1 and R1, as we have already indicated, and I2 and R2 respective angles of incidence and refraction at points P and Q respectively. Points P and Q are on faces, the first face and the other face. We can call this X y, z. That is our prism. Then we can say if I1 and R1 and I2 and R2 are respective angles of incidence and refraction at points P and Q respectively on faces XY and YZ, on faces XY and YZ, and N. This prism, take it to have a refractive index N, and N is the ref index of the prism. The prism is XYZ now, and N is the ref index of the prism. Then, using our N sin I is a constant. N sin I is extremely important in the physics of refraction of light. Using our N sin I is a constant, we can say that at point P, the N of air times the sine of I1 should be equivalent to actually the N of glass, that is the prism, times the sine